Hello everyone, welcome to the Easy Power Thursday Technical Webinar Series. Today's topic is the challenges to designing DC protection systems for electrical vehicle charging. And before I introduce our guest speaker, my name is Jim Chastain and I'm your host for today's session. We are in the habit of extending poll questions to get a little bit of feedback from the audience before we start. And if you would be so kind as to participate. Our first question is, what has been your experience with electrical vehicle charging design? Looks like we have a quorum on this question. Here's how everyone has responded. All right, looks like we have the right audience for the presentation. Second question is, what DC voltage ranges would you most often utilize or anticipate utilizing? Really looking forward to the presentation. This has been highly anticipated by a large number in the audience. Or so folks have responded to that question. Good. Thank you very much. And then finally, what experience or exposure do you have to protective devices for this type of system? This is where we probably will get a wide variation in responses. Our guest speaker joins us from Bergamo, Italy today, and we appreciate his commitment to the presentation greatly. Here's how we've gathered the responses here. And again, thank you for participating. And at this time, I'd like to hand the baton over to Marco Carminetti.
Yeah.
Okay, Marco, you have the baton.
Okay. Thank you, Jim. Good morning, good afternoon, everybody, also from my side. Welcome to this webinar from Italy, in Bergamo. As Jim already introduced, today we talk about the challenges and during the design of DC electrical vehicle charging infrastructure. I mean the capability to supply our DC chargers already in DC. And in particular, we will talk about the faults, both short circuit and ground fault that can occur in this infrastructure, and what we have to take into consideration during the design phase in order to protect this infrastructure. So, first of all, as you can see in this slide, in particular from the bar diagrams, from the 2019 till and up to 2030, there will be an increase of the total number of DC charging points installed worldwide. In particular, they are used for the so-called fast DC charging. And as you can see on the right, more than 70% of the charging points are basically in DC. So the question now is, why don't we supply directly the DC charger in DC instead of AC? Here you can see the two typologies of EVCIs, electrical vehicle charging infrastructures. So when we talk about charging infrastructure, basically we talk about a low voltage distribution system starting from the medium voltage, low voltage transformer installed inside a cabinet, inside a sub-distribution system, which is connected directly to the medium voltage AC utility. Then we can have the low voltage distribution system in AC, usually at 400 volt AC or 790 volt AC for IC application or 600 volt for UL application. This sub-distribution system is used in order to connect in parallel the DC chargers, which embed the so-called AC-DC converter. And then we can have one or more distributed energy resources in order, let's say, to supply directly the electrical vehicle with renewables and with some batteries system in order to be able to guarantee a continuous supply, even if, for example, we have the, let's say, renewable not available, for example, during the night for the solar system or in a no windy day for the wind power plant. Here, as you can see, is a typical AC microgrid. So if you'd like to supply the DC charger directly in DC, also because, as you can see here, photovoltaic system and battery system are already in DC. For the wind power plant, you know, we can use a variable frequency generator, and instead of having a double conversion to, let's say, supply our distribution system with a fixed frequency, 50 or 60 Hertz, instead of having a double conversion system, we can have just a single rectifier. So we can move from the previous configuration to this one. As you can see, we have a main so-called front-end AC-DC converter, which interfaces the local distributed generation and the local loads with the medium voltage AC utility by means of a medium voltage common transformer. And then we have locally the same generation, but now this local generation is connected by means of a single rectifier or a single DC-DC converter in order to adjust the local production with a fixed voltage to the rated voltage of our distribution line. And here, if we talk about a low voltage distribution system, so far the maximum voltage is up to 1500 volt. But here is up to the designer to decide which could be the rated distribution voltage. And then inside the DC charger, instead of having an AC-DC rectifier, we can have a DC-DC converter, which is usually simpler, and in terms of efficiency, usually it has a higher efficiency compared to the AC-DC rectifier in both the configuration, I mean non-isolated and isolated configuration. So here you can see a typical single line diagram of DC electrical vehicle charging infrastructure. So starting from the right, here we have the schematic of an electric vehicle connected to the DC fast charger, which is represented by the internal battery in series with a protective devices, which is usually a fuse, in order to be able to detect and interrupt the short circuit fault. Then we have the DC charger, which is represented by a DC-DC converter, which can be a non-isolated or isolated converter, as we'll see later on. Then we have in series a switching device, usually a switch is connected, not to be able to disconnect also the circuit in so-called load condition, so with current, in series with a protective device also in this case, usually an internal fuse. Then, in order to connect these DC chargers in parallel, we can have one or more DC combiners, and in a very large scale DCI, we can have also the so-called DC recombiners, like for example, we have in a large DC photovoltaic plants. And then we have one or more main AC-DC converter. We see later on the internal architecture of this AC-DC converter. Usually, this AC-DC converter has to be bidirectional in order, let's say, to allow the battery charging, but also in the so-called electric vehicle to grid function. So in order to be able to inject in some cases the power also into the AC grid, this AC-DC converter can be bidirectional. And then we have the connection with the medium voltage AC utility by means of a typical and common medium voltage low voltage transformer. So let's talk about faults now that can occur in our DC infrastructure. If we talk about DC short circuit, where are the typical fault locations? We can have basically the fault A in this section between the main AC-DC converter and the DC recombiner. The fault B, a short circuit that can occur between the DC recombiner and one or more DC combiners, and a fault C, which usually occur between the DC combiner and the DC fast charger. So let's talk about, first of all, fault A. If we would like to talk about fault A, we have to consider, as I was saying, first of all, the internal architecture of the AC-DC converter. There is a conventional wisdom for which if there is an AC-DC converter, the fault is no more an issue. This, let's say, statement is true in some cases, in particular if the fault occurs on the AC side of the converter. But if the fault occurs on the DC side of the converters, this statement is not always true, and it depends on the internal architecture of the converter. So, for example, if we consider a thyristor rectifier, and if we have a DC short circuit, the DC short circuit can be limited and controlled by not sending the so-called closing command to our thyristor. So in this case, is it true that if we have a DC short circuit, we can limit the DC short circuit by means of the AC-DC converter itself. But this type of converter can be used only in not bidirectional mode, which means only if we have to, let's say, deliver the power from the AC grid to a motor, or in our case to the electric vehicle batteries, but not vice versa. So we cannot inject the power into the grid in the so-called vehicle to grid function, because here, in order to have a reversal power flow, we have to change, let's say, the polarity of the voltage applied to our system, because if you would like to have reversal power, we have to change either the voltage polarity or we have to change the current. Inside the thyristor, we cannot change the current, so the only way is to change the voltage polarity. But you know we cannot change the voltage polarity inside the DC system, because if we have both loads or battery system or any local generation, by changing the voltage polarity, we can create very big issues on our system, and in some cases also a very dangerous short circuit, for example, if we have batteries applied to our system. So if you'd like to have a bidirectional system, we have to use the so-called IGBT-based AC/DC converter. IGBT-based AC/DC converter is bidirectional, so the current can flow from the AC grid to the DC microgrid to our VCIs and vice versa. But if we have a DC fault, as we see in the following slides, we are not able to neither to limit nor to interrupt this short circuit current, since the current will pass through the freewheeling diodes embedded inside the converters. You know, we can control the IGBTs since they are semiconductor devices. Basically, they can be controlled both in open and in closed position, but diodes cannot be controlled. So imagine to have a short circuit on the DC side of our DC distribution system. Then we can have an overall load, or like in our case, we have more than one battery installed in parallel, here represented by a voltage generator in series with the internal resistance. And we can have also, for example, a photovoltaic system installed in our DC distribution system in order to supply locally the requested power or part of requested power. If we have a short circuit on DC side, imagine the worst case with a fault resistance negligible, practically equal to 0, apart from the resistance of the cable connection. As you can see, we can have a triple contribution. The first one is the blue dot line contribution coming from the batteries installed on our vehicles and passing through the DC chargers according to the internal architecture of the DC-DC converter, as we can see later on. And then we can also have the contribution coming from the photovoltaic system, even if, as you know, the contribution coming from the photovoltaic system usually is quite limited to a value close to the rated current of this photovoltaic system. But if the DC-DC converter installed inside our DC charger is not able to limit the current, the fault current, we can have a huge contribution coming from all the batteries of our electrical vehicle installed in parallel at that moment. Then we have a green dot line contribution, which is the contribution coming from the DC capacitor discharge current. Usually when we have a CDC converter, we can have a huge capacitor on DC side of tens of millifarads. So we can have a huge DC capacitor discharge current peak up to 300,000–400,000 amp, lasting usually less than 1 millisecond, but can be very huge. And then we can have the AC grid contribution passing through the freewheeling diode, which cannot be limited and interrupted. And as you can see from this formula, practically this DC contribution coming from the AC grid is equal to a prospective AC short circuit current contribution that we have at the input of our AC/DC converter. For example, if on the AC side of the converter we have a prospective short circuit current on 50 kA, practically this value of current contribution is the same on the DC side. So we need some suitable protective devices in order to be able to detect and interrupt this short circuit. If we have a DC-DC converter installed, for example, between a photovoltaic plant or between the batteries installed on our vehicles and the DC distribution system, according to the internal architecture of this DC-DC converter, we can limit or not the contribution from the local generation and from the batteries of our electrical vehicles. If these DC-DC converters are the so-called step-down converter or buck converter, this means that the output, the voltage on the output is lower than the voltage on the input. So here, if with R we represent not a load, but for example, the batteries of our vehicle here, and if the fault occur on the vehicle side, our DC-DC converter is able to limit this current because, as you can see from the current path, we can open the IGBT installed inside the DC-DC converter. But if we have a fault on our microgrid, the battery is able to supply this fault since the current contribution is passing through the diode and we are not able to limit this contribution. The same thing if we have, for example, a so-called step-up converter or boost converter. So the voltage on the output of the converter is higher than the voltage of the input. So imagine here the input is, for example, the PV plant or the battery of our system, and the output is a microgrid. If you have a fault on the microgrid, we cannot limit this current because the current is passing through the diode D1. The same thing if we have a bidirectional DC-DC converter, which is normally used in VCIs with, as I called them, the vehicle-to-grid function. So, in order to guarantee the injection of the power into the grid, we have to install the bidirectional AC-DC converter and also DC-DC converter. So, if we have a fault on a DC microgrid in a step-up configuration, as you can see, according to the internal architecture of the converter, we cannot limit this contribution since the current during the fault is passing through the diode D1. So in the second and the third configuration, we have to install on the left or on the right, this means on the input or on the output of our converter, a suitable protective device in order to be able to detect and interrupt this contribution. If we have a so-called isolated converter, this means that inside our converter we have a transformer in order to guarantee the galvanic isolation of the system. As you can see, if we have a fault on a DC side in a DC-DC converter or on the output of a DC-DC converter, imagine for example that the output is our local DC microgrid, so our local DC distribution, we can avoid the contribution from the AC side, for example, on the left, for the steady state contribution, but we have still the DC capacitor discharge current in both configuration, AC-DC converter or DC-DC converter. What does it mean? It means that we have still to install on the DC side a suitable protective devices in order to be able to detect and interrupt this short circuit contribution coming from the DC capacitor discharge. So here on the left we have the summary of the three contribution coming from the AC grid, the DC capacitor, and from the local generation of the batteries during a short circuit, generally speaking, in our system. But if we have a fault in A, we have the contribution coming from the AC grid and the DC capacitor. And here, let's say the blue contribution is made by all batteries installed in parallel in that point and connected to the DC chargers. So here the contribution is, let's say, proportional to the number of batteries. The higher the number of batteries, the higher the total contribution coming from them. If we have a fault in B, for example, between the DC recombiner and C combiner, here you can see that this red line is the contribution coming from all the batteries installed in the other, let's say, n-1 DC combiners installed in parallel, plus the contribution coming from the AC grid and the DC capacitor. Instead, if we have a fault in the point, at the point C, we have the same contribution of fault B plus the contribution coming from n-1 batteries installed in parallel in the same DC combiner. So as you can imagine, here the contribution is higher than the contribution in B. And according to this prospective short circuit current, we have to select the protective devices having a breaking capacity higher to this prospective short circuit current. Otherwise, the risk is not to be able to interrupt this short circuit current in case of fault. If we have a ground fault, basically the probability to have a ground fault is higher at this point. This means directly on board of the vehicle and between, let's say, the internal architecture of our DC charger and the exposed conductive part, if the, let's say, the chassis of the DC charger is not made by an insulating material. So if we have a ground fault, here we have to consider the ground connection of a medium voltage low voltage transformer. Here we consider a non-isolated converter, because if we have an isolated converter, both the AC-DC converter and the DC-DC converter, we don't have a ground fault. But in case of non-isolated one, for example, usually it is quite common to have a DC-DC isolated converter, I mean, at least inside the DC charger. But in order to reduce the installation cost, in some cases we can have as a main AC-DC converter the isolated one. So in case of a short circuit, ground fault on a common load, or here instead of having a load we have our batteries installed on our vehicle. Here we can have, if the vehicle is connected to the PE system, so is not ungrounded, even if the battery is installed on our vehicle is ungrounded in terms of active part, we can have a reclosing path through the the neutral point connection to the ground of our medium voltage low voltage transformer, in particular of the low voltage windings, if they are connected to the ground. As you can see, also in this case, we can have a triple contribution. The contribution coming from the DC capacitor discharge current passing through the lower IGBTs installed in our converter, the batteries contribution and photovoltaic contribution coming from all the other batteries installed in parallel at that moment and still passing through the lower IGBTs, and we have still the contribution coming from the AC grid but passing through the upper freewheeling diodes. Here, without considering the so-called IGBTs internal and embedded protection. If we consider the internal IGBT protection, in case of a short circuit, it is a total ineffective because as I said before, in case of particular bolted DC short circuit, the currents passing through the freewheeling diodes. So even if we rely on the internal IGBT embedded protection, is totally ineffective. So we are not able neither to limit nor to interrupt both the AC grid contribution the contribution coming from the DC sources. Instead, in case of a ground fault, as you can see in this schematic, if we rely on the internal IGBT protection, we can open the IGBTs, which means that we can interrupt the contribution coming from all the other battery system in parallel, batteries of electrical vehicles, if the DC-DC charges are not isolated, and also the contribution coming from the DC capacitor. But we have still the contribution coming from the AC grid passing from the upper freewheeling diode. So we still need on the DC side of suitable protective devices. In case of an isolated AC transformer windings and we have a connection, for example, of the midpoint, DC midpoint to the ground. In this case, we don't have the converter contribution to the ground fault anymore, but we have a transient contribution coming from all the other batteries installed in parallel, and if we have also the photovoltaic system connected or any other DC sources with a non-isolated interface converter. But we have a negligible steady-state ground fault current. Here the big issue is the voltage towards ground of our positive and negative polarity. In particular, if we have a fault, ground fault between positive and negative with a negligible ground fault resistance, here the voltage towards ground of a faulty pole, as you can see here, is, let's say, practically equal to 0. The problem is on the earthy polarity, since the voltage moves from half the rated voltage to the rated voltage, which means that the voltage towards ground can increase twice, I mean 2 times the half the rated voltage in normal operation, and it can create a big issue to the isolation system of our cables of or any other isolation system installed in our switchboards. If we have a fault, ground fault, as I said, at this point, as you can see, we have a contribution coming from the grid and the contribution coming from all the other batteries installed in parallel, which can be interrupted, as I said, by the internal protection of the IGBTs. But still, we need a protective device in order to be able to interrupt the contribution coming from the grid. So, talking about the possible switching and protection architecture, we can have 3 main philosophies. First of all, we have the traditional configuration, as you can see, made by the traditional switching and protective devices. A circuit breaker, molded case circuit breaker, or switches connector plus fuses, and miniature circuit breaker installed inside our DC charger according to the rated charger of rated power of the chargers. We can have also molded case circuit breaker, and fuses installed inside our electric vehicles. Here we can have a double issue. I mean, first of all, if we have, for example, a fault at this point, we have a contribution, as I said, coming from all the others batteries installed in parallel. But here is not able, we are not able to guarantee the selectivity between this circuit breaker, which is usually a circuit breaker, and the internal fuses, in particular the so-called ultra-fast fuses. So we can have the shutdown of a complete system if we have a fault at this section, or for example at this section. Furthermore, we are not able to protect the internal freewheeling die of the converter because the let-through energy passing through this air circuit breaker is not low enough to protect the internal freewheeling diode. So we can have also in that case the damage of the main AC/DC converter. The second architecture is a sort of hybrid architecture where we have a main so-called solid-state circuit breaker. This is a new technology of circuit breaker, and we have just developed this type of circuit breaker. This circuit breaker is very, very fast. So in case of a short circuit at every point of this architecture, this circuit breaker is able to both detect the short circuit contribution coming from the DC capacitor discharge and from the DC grid. This means that it is able to reduce the current peak coming from the DC capacitor, and also it is able to protect the internal freewheeling diodes of the converter. Last but not least, we can have the so-called total solid-state configuration, where we install everywhere, apart from the DC charger, on our DC bus and inside the DC recombiner and DC combiner, the solid-state circuit breaker. So we are able to guarantee the selectivity among the solid-state circuit breaker by means of a fiber optic cable connection. And if you have, for example, a short circuit here, since this solid-state circuit breaker is faster even than the fuses or ultra-fast fuses installed on our vehicle or inside the DC charger, we are able to guarantee the not shutdown of the complete system when we have a fault on a single section of our system. So in terms of selectivity and service continuity, we can have a very, very huge advantage. So what do we can offer as ABB for this type of electric vehicle charging infrastructure? Here, as you can see, and you can go deeper in detail on our website, here we have a full range of let's say traditional component, I mean electromechanical component for switching and protection, so capability to switch also the current and to guarantee the galvanic isolation in open position, switch-based and breaker-based. Breaker-based is also the capability to have a remote tripping, I mean to open and close the switches connector by means of a shunt opening release, and also close by a motor operator. We have also a contactor, which is normally can be installed on the DC charger in order to guarantee a higher number of operation in load condition, I mean with the current, and also circuit breaker in both so-called air or power circuit breaker with electric current up to 5,000 amp at 1,000 volts, and also circuit breaker in a so-called molded case configuration with a lower electric current, but with a higher number of operation in load condition. Here, I would like to introduce you to our new development, the first real solid-state circuit breaker called SACE Infinitus. So it is a full solid-state circuit breaker And here you can see the advantages of this circuit breaker that you can see on the right. It is 100 times faster than the traditional circuit breaker, having the same rated current. Just to give you an idea, if we talk about a near or power circuit breaker, the interruptive time is tens of milliseconds. Here we are talking about an interruptive time of 100 microseconds. So, as I said, is 100 times faster. Also, in terms of the capability of interrupt the current, the circuit, we have 10 times the number, sorry, 100 times the number of the operation in load condition. Near zero arc energy exposure, because thanks to its very fast interruptive time, we can limit the energy released during an arc flash event, so we can reduce the arc flash hazard. Compared to other existing solid-state technology, here, thanks to the internal architecture made by IGCT, which is the integrated commutated gate for commutated thyristor, it has a lower power losses compared to, for example, other technologies like IGBTs. And here, thanks to this solid-state circuit breaker, we can enable the DC distribution inside any DCI, but also, for example, inside buildings, also on board of ships. Here, the main characteristics of this circuit breaker, so far the frame size is 2500 amp at 1000 volt, but we are still thinking about frames with a higher value of current and also with a lower value in order to be able to enable the total DC distribution, also considering a feeder having a lower current, for example, supplying a DC chargers. Here, the opening time of 25 microseconds, it is the opening time of the internal IGCT's internal semiconductor. Then the current goes to zero through the so-called metal oxide varistor installed in anti-parallel to our semiconductor in order to limit the overvoltage and in order to allow, let's say, a smooth, let's say, that the current goes to zero in a smoothly way. Here, the power losses, which is very, very lower compared to other technology, which usually is up to 4 or 5 kW. It is a liquid-cooled version in order to limit the space and the total volume of this circuit breaker. And here you can see the schematic of internal architecture. So two IGCT in anti-parallel, then we have metal oxide varistor in parallel, inductance in series in order to be able to limit the current and to guarantee the breaking capacity, and a DC-20 disconnector in series in order to guarantee the galvanic isolation open position, because you know the semiconductor are not able to guarantee the galvanic isolation since there is no the fixed and mobile contact like in a traditional disconnector. In order to guarantee a different breaking capacity, we can have, we don't have the internal inductance. We can have an internal inductance on 3.5 microhenry, and we can have the internal inductance plus an external additional inductance in order to limit and to guarantee the breaking capacity up to this value of basically current derivative. Unlike the traditional circuit breaker, where we have a breaking capacity instead of tens of hundreds of kA, Here is not a matter of the steady state value of the short circuit current, but it's a matter of derivative. For example, if we can have a prospective short circuit current up to 1 million amp, but if the derivative of the current, so according to the total time constant of the system, is lower than 80 amp on microsecond, here we are able to interrupt a sort of unlimited prospective short circuit current. So that's all from my side. Here you can find by my contact in terms of email and phone number. And here some link to our website where you can find more information regarding our portfolio, our application, in particular this application that we are focusing on, and some more information regarding the new development in terms of solid-state circuit breaker suitable for DC application, which is able to protect the DC-DC converter and also to detect, in particular, the DC capacitor discharge current. That's all from my side. Now we thank you for your attention, and we can go now to the Q&A session.
Good job, Marco.
Okay, so here, first one, here. What is the advantage of using DC combiner when not connected DC charging directly to the DC recombiner? Yeah, here there is no, let's say, a single way to connect our DC charger. I mean, also according to the rated power of our system, usually the higher the rated power value, the higher the number of DC combiner, and we can have one or more recombiner, or we can connect directly our combiners to the AC/DC converter. But if we don't have a recombiner, so if we connect, for example, 10 combiners to our AC/DC converter, we can have 10 DC input to our converter, which means that we have to install inside our converters 10 switching and protective devices on each feeder coming from the DC combiner. So it's up to the designer to install these switches inside the so-called PCS, power conversion system, instead of having a single DC bus coming from the DC recombiner, where we have let's say, switching and protective devices. ABB circuit breaker has application on railway DC traction power system. How possible the arc-chute mechanism can be elaborated a bit more? Yeah, here for traction system, here we are talking about, in a lot of cases, a voltage higher than 1500 volt. We can use also the DC breakers for railway application also in EVCI. But here, if we consider a voltage lower than 1500 volt, we can use a traditional circuit breaker for low voltage application. But if we would like, as I said, to protect against the short circuit, and in particular to protect the converters, because historically in the railway application we often used the thyristor rectifier, and in that case we were able to interrupt the short circuit by means of the let's say the internal capability of a thyristor. But now if I use the JBTs, in particular in the so-called bidirectional application, here it is better to use a solid-state circuit breaker in order to be able to protect the converter itself, and also in order to detect the DC capacitor discharge current. You know, DC capacitor is practically installed always on the DC side of a IGBT-based converter, because they are used to limit the DC voltage ripple. they are a huge capacitor in terms of value. I mean, tens of millifarad. So they can provide a very huge current peak. But since this current peak lasts low than 1 millisecond, with a traditional circuit breaker, in particular open or power circuit breaker, we're not able to detect this current. In some cases, also ultra-fast fuses are not able to detect this current, and in particular to limit the current to a value low enough to protect the internal triggering diode. So we need the solid-state circuit breaker. Why can't we standardize all the EV chargers around the world? You did this with a cell phone. A very, very good question. To be honest, I don't know. I mean, I am part of some IC standard committees, and now we are, let's say, working on the definition of the DC system. I mean, in terms of ground fault connection and ground fault naming. For example, you know, in the past there was TT, TN, IT naming for the AC system. Now we are studying the naming for the hybrid AC/DC system. So far, there are a lot of DC chargers and also fast and ultra-fast DC charger, but they are still connected to the AC part. So inside they have a AC/DC converter. As ABB, we are developing, or at least we are already looking at a so-called DC/DC charger, but there is not a standardization so far, unfortunately, at worldwide. Will slide be provided to attendees? Yes, for sure. In terms of budget, how much it would be a 350 kW charger station with a this protection configuration, supply charging facility? Here it depends on the type of circuit breaker that we use. I mean, if we use the traditional circuit breaker, I mean, here with this value of power, here we should have to make some maths. But maybe here there will be a main power circuit breaker, I mean, open circuit breaker of 1,000–2,000 amp, and some multi-case circuit breaker installed on the feeders coming to a DC combiners. So here, to be honest, just to give you a rough idea, we are talking about tens of €1,000, $1,000, roughly, talking about the switching and protective devices. Then we have to consider the CDC converters and the DC chargers. And then, if you'd like to use also a solid-state circuit breaker, here obviously the cost increases due to, in particular, to the benefit and the added value that we can be able to provide our customer with. I don't see any other question. Anyway, if you have any doubt, any more questions, you can reach me out also in the next days by mails or by phone, and it will be my pleasure to reply you. And if you have any project, also any pilot project, and would like to get any support from myself or from my colleagues working in my department on DC application, please let me know, and you will be more than welcome.
Thank you, Marco, for the presentation.
Yeah.
Thank you, everyone, for attending, and we will see you in future presentations. So long.
Yeah. Thank you to all of you for your attending, for your attention. Please have a look to my presentation, and as I said, if you have any doubt or something is not clear, please reach me out.